master's thesis, which I just completed, in April under the supervision of my supervisor, Dr. Bernardo, at TMU, and it's a slight extension on the topics that were broached in the paper towards this conference. Oh, not sure. Computer, yeah. I might just use the arrow keys. Yeah, that's fine. Use the arrow keys. Yeah, so tournaments or oriented complete graphs, they represent highly dense networks, especially in contexts where there's some sort of competition between the nodes. So a classic example is that of round robin tournaments in a game or sport where there are no ties between players. So an arc from player A to player B just indicates that player A defeated player B. Another example is that of paired comparisons. So say you want to glean something about a consumer's preferences with respect to a particular type of product. An arc from brand A to brand B would indicate that given a choice between the two brands, the consumer tends to go for brand A over brand B. And finally, tournaments may also be extracted from online social networks. So an arc from user A to user B might represent that user A has more views, likes, or follows than user B. It can also indicate that user B has engaged more with the content generated by user A than the other way around. So looking at the structure of these tournaments, we might get some insights into how a new piece of information or opinion might be passed around throughout the network. So here's an example, a very simple example of a tournament on 7 vertices. It's 3 regular, so each vertex has 3 out neighbors and 3 in neighbors. And this kind of tournament might represent a small clique, in a social network where the users are talking among themselves about a very specialized topic, and they have about the same amount of influence over each other. So the model that we're going to be considering over here will generate tournaments with some key properties of complex networks. So they will be evolving, they'll be large, and they'll have but they'll still have bounded average distance and diameter. So they're a small world. And we'll be using the principle of transitivity to generate these tournaments. So this is an organizing principle we see in places like trust networks, in online shopping, for example. So, if you have a bunch of users sharing their opinions about the products that they're buying, if user X trusts the opinion of user Y and user Y trusts the opinion of user Z, you would expect typically that user X should also trust the opinion of user Z. So I'll move now to the formal definition of this model. So starting with a tournament G, you define this new tournament G sub 1 with the overwrite arrow as follows. So for each vertex X in G, you add a new vertex X prime called its clone. And then you're just copying the structure of G within this new tournament. So for each arc X to Y in G, you add the arcs X prime to Y, X to Y prime, and also X prime to Y prime. And to ensure that what you're getting is indeed a tournament, you also have to choose an orientation for the edges incident on X and X prime, right? So in this case, we take the arc from X prime down to X. And then for each time step t greater than or equal to 0, given G sub t with the overwrite arrow, you can define G sub t plus 1 with an overwrite arrow just by repeating this process over and over again. And we call G sub t with the overwrite arrow the T transitivity tournament or ILTT tournament generated by G. We'll also consider a slight variation on this model. So we can define G sub 1 with an over left arrow from G by essentially applying the same process, except that among the clones, when X to Y is an arc of G, we don't add X prime to Y prime. Instead, we add Y prime to X prime. So among the clones, you have the dual of the base tournament G. And of course, G sub T with an over left arrow, we'll call that the dual transitivity tournament, the Tth dual transitivity tournament generated by G. So here's an image of what happens when we start with a 3 cycle as our base tournament. The middle image shows the first transitivity tournament generated by that 3 cycle, and the rightmost image shows the dual transitivity tournament generated by that 3 cycle. They're pretty much the same, except that among the clones there, A prime, B prime, and C prime, the orientations are reversed. So even though these two models are pretty closely related, they behave quite differently with respect to certain properties. I've mentioned that they will have bounded diameters. So specifically, if you start with a strong tournament on with diameter 3 or greater, then yes, every transitivity tournament that it generates will also have that same diameter, right? So they have this dependence on the diameter of the base tournament. It's just in the case where the diameter of the base is 2 that the first transitivity tournament has diameter 3, and then after that it's just constant. In the dual case, this dependence on the base disappears. So yes, if the base has diameter 2, every dual transitivity tournament it generates will also have diameter 2. But in every other case, no matter what the diameter of the base is, it'll only generate diameter 3 tournaments under the dual process. So let's just verify really quickly that if you start with a strong tournament, these processes do give you strong tournaments. We'll make use of this result of Kamyan's that a tournament is strong if and only if it's Hamiltonian, meaning there's a cycle passing through all of its vertices. And in our case, it turns out that if you start with a Hamiltonian tournament, it generates Hamiltonian tournaments under either process. And this image here shows us quite simply why that is. So these dashed arcs represent a Hamilton cycle in the base tournament G, and then you can trace out a Hamilton cycle in the transitivity or dual transitivity tournament it generates by simply following these dashed arcs, but instead of going to the next vertex, you first hop over to its clone and then down to that vertex. So average distance also behaves quite similarly to diameter. So if L of G is the diameter, sorry, average distance of a tournament G on n vertices, then as T goes to infinity, like asymptotically, the average distances of transitivity tournaments are equivalent to this expression over here, 2 plus n minus 1 times the average distance of G over n. So if n is large, then it won't deviate much from the average distance of the base. Again, in the dual model, this dependence on the base tournament disappears. No matter what the average distance of the base is, asymptotically, the average distances of the dual transitivity tournaments will approach 3 over 2, with equality holding when the diameter of the base is 2. So in the second part of this presentation, I'd like to move to this question of spectral properties of transitivity tournaments with a view towards spectral ranking. So given the adjacency matrix A for a tournament G, we can get the adjacency matrix for G sub 1 with the overwrite arrow, meaning the first transitivity tournament, by this block matrix A sub 1 over here. And these instances of A in the blocks are just referring to the fact that we're copying the structure of G in this new tournament. The plus I identity matrix is referring to the fact that we're adding arcs from clones, X prime down to X. So it turns out that if you start with a non-zero eigenvalue lambda for A, this expression for mu in terms of lambda gives us 2 eigenvalues for A sub 1, depending on which sign you choose in front of the square root. And if V is an eigenvector of A associated with lambda, then this expression in terms of V and mu will give us an eigenvector of A sub 1 associated with mu. And it turns out these are all of the eigenvalues for A sub 1. Sorry, all the non-zero eigenvalues. So we can now apply the Perron-Frobenius theorem for non-negative irreducible matrices. In particular, for strong tournaments, it tells us that the spectral radius of the tournament is indeed an eigenvalue of the tournament, and it's positive. So it's a positive real number, and its eigenspace is generated by a unique unit vector with non-negative entries. And in fact, it's the only eigenvalue that has this property. So for any other eigenvalue, there is no eigenvector with just non-negative entries. And so given the earlier characterization of the spectra of transitivity tournaments in terms of that of the base, we're interested in this function f defined for complex numbers. So if rho is the spectral radius of your tournament G, then f of rho has to be an eigenvalue of the first transitivity tournament it generates. And if v is the Perron vector for G, then this expression in terms of v and f of rho is an eigenvector associated to f of rho. But because it also has to have non-negative entries, this f of rho is indeed the spectral radius of the first transitivity tournament. And then proceeding by induction, we can get that, so that if you take a t-fold composition of f and evaluate it at rho, you get the spectral radius of the tth transitivity tournament generated by G. So going back to this example of the three regular tournaments, if you use this as your base and you proceed to apply the transitivity process to it 7 times and you plot their spectra, you get this image over here. So the top left is that shows on the complex plane the eigenvalues of the three regular tournaments, and then the subsequent ones are eigenvalues for transitivity tournaments that it generates. And what you'll notice is, so in general, for regular tournaments, its spectral radius is a positive real number, of course, but then every other eigenvalue lies on the line where the real part is -1/2. And the function f that I defined earlier, right, that's invariant. So the line real part equals -1/2 is invariant under that function, and no complex number outside of that line is mapped into it. So what you're seeing here is just that all the eigenvalues on the line real part equals -1/2 are being mapped to that line itself, and the only other eigenvalues that you're seeing are in the orbit of rho, the spectral radius of the regular tournament, under compositions of f, and also the version of it where you take a negative sign in front of the square root. And so finally, we can talk about the Perron or Kendall-Way ranking of these tournaments. So if you take the Perron vector of the tournament G, you can associate the ith component with the ith node in that tournament as a kind of score. And then the ordering of these nodes from highest to lowest score is what we call the Kendall-Way or the KW ranking of the vertices in the tournament. And it's known to be a measure of sort of the relative strengths of the nodes in terms of their influence. So it takes into account not only the number of outneighbors that a node has, but also the number of outneighbors its outneighbors have, and so on and so forth. The variance of the KW scores will then tell us, how equitably is influence distributed across the network, right? And in particular, for a tournament G on n vertices with spectral radius rho, the variance simplifies to this expression over here, n minus 1 minus 2 times rho over n times n minus 1. And we can apply this expression to the transitivity tournaments, right? So n will just be doubling with each step. And you can see that in fact, the variance of the KW scores is going down to 0. So over time, you're getting this kind of smoothing of influence. It doesn't preclude the existence of highly influential individuals, but overall, there's kind of an equitable distribution of influence across the network. And so just to close off some grounds for future work, I wasn't really able to find a characterization for the eigenvalue spectra of dual transitivity tournaments. The computations are kind of confounded by this transpose of A in the bottom right block. So that would be interesting to look at. And then also, I'm very well aware this is a deterministic model. In situations, if you want to apply it to a situation where there's a lot more noise, randomness, maybe you want something that's stochastic. So maybe looking at a version of the model where you apply either the transitivity process or the dual transitivity process with some probability p, and see what you get from doing that over and over again. And yeah, that's all I wanted to talk about. Thank you very much.